Today we will be exploring how a cyber attack on a space launch may occur, what impacts it could have, and how to defend against it. Space plays a critical role in everyday life in the modern world. The launch event is a critical choke point when it comes to access to space for a nation or a private entity. There are significant geopolitical advantages as well as significant opportunities for profit involved with every space launch. An attack on a launch event can have results that range from delays to the loss of the launch vehicle and the payload. Space launches are monitored very carefully to prevent damage to life, property, and wildlife. During the launch, the rocket's trajectory is continuously compared to the planned trajectory. If the rocket deviates from the expected trajectory enough, the rocket will be destroyed. Traditionally, this function utilizes people to monitor the rocket telemetry and make the decision to destroy the rocket or not. The Autonomous Flight Safety System, or AFSS, removes humans from this loop. The AFSS is intended to increase safety and reliability of the launch systems. By utilizing the AFSS, launch costs can be decreased while launch cadences increase. The AFSS hardware consists of heavily redundant components to ensure extremely high reliability. The AFSS software itself is based on simple rule systems that consist of mission rules, mission data entities, and mission modes. Depending on the threat actor, a rocket launch is vulnerable to a variety of attacks such as ransomware, signal jamming, or malicious code injection. Different threat actors will have different motivations as well as different capabilities. The Sparta framework by Aerospace can be used to understand what a malicious AFSS code attack on a space launch would look like. Starting with the reconnaissance, the threat actor would need to obtain the AFSS source code through a means such as social engineering or obtaining it through the darknet. Using Sparta Framework, Rec 0004.01 provides countermeasures to a threat actor that is trying to obtain information regarding the space vehicle termination system. Protecting sensitive information is the primary countermeasure against this reconnaissance. The threat actor then would use the gathered information to exploit code flaws and craft malicious AFSS code. Defense against this would include threat modeling and/or vulnerability scanning. Armed with the malicious code, the threat actor will need to be able to inject this malicious code into the AFSS system. One way to do so would be to compromise the assembly, test, and launch operation of the spacecraft and launch vehicle. With a variety of methods to defend against these threat actors, we could employ tamper protection, insider threat protection, and physical security controls to decrease the chances of software compromise. A successful execution of this attack would result in the rocket self-destructing because it believed it was off the planned trajectory. This would be accomplished by the malicious code either modifying onboard values or spoofing the telemetry data from the AFSS sensors. To effectively defend against this, having onboard intrusion detection and prevention systems, having robust fault management, and also a cyber safe mode would be highly beneficial. Here are several examples of failed launches that demonstrate how critically successful space launches are to the nation, as well as private entities. The damages of a failed launch could be the denial of a capability, wasted funds, or a drastic drop in stock price. Space launches have a large surface area of attack, and autonomous safety systems add to that surface area. Interference in the launches can have a large impact on access to space and the cost of that access. Not paying the right attention to cybersecurity of a space launch can result in successful attack and launch failure. Prevention and detection methods should be investigated further to ensure that attacks can be successfully mitigated and AFSS can provide the launch cadence increase and launch cost decrease that it is intended to, rather than being a vulnerability.